Okay, so for today we have chapter 11, and starting this chapter, we are focusing on stars. We're done with planets, we're done with asteroids and comets, so all of those leftovers from the process of the formation of the solar system, not interesting anymore. We really want to focus on the main object in our solar system. It's called solar system because there is a sun. It's the system of the sun, literally. And this is our main power plant. It generates a hell of a lot of energy. It supports life, and not just on Earth, but all the other planets receive uh, energy from the sun in the form of radiation and thermal energy. And uh, it turns out that the sun is just one of many. The sun is nothing special. It's kind of an average star by many parameters. There are stars that are way more luminous, way less luminous, way more massive, way less massive, and so on. So the sun is somewhat in the middle. It is a main sequence star, which we'll discuss in the next chapter. And understanding what's going on uh, within the sun and on the sun gives us a chance to think about other stars and galaxies that are made of stars. So you definitely understand the universe through understanding the sun. So it is a glowing ball of plasma. Plasma is ionized gas. It's a gas with a lot of electricity running in it. And the main components, the main gases are the hydrogen and helium, mostly hydrogen, of course. And you can see that size-wise, it's 100 times the size of the Earth. And mass-wise, it's 300,000 times the mass of the Earth. You really can't even compare the Earth to the Sun. The Sun takes 99% of all the mass in the solar system. Okay, combine all the planets, all the asteroids, all the evil aliens, it's only 1%. Okay, and the sun takes the rest 99, like 99.7, I believe, percent in terms of mass. And because of that, we have enormous gravitational field, and with that gravity, all the planets, all the asteroids, all the evil aliens orbit the sun, and the sun is pretty much just sitting in the center. The power output, the amount of energy that it generates in 1 second, it's 3.8 times 10 to the power of 26. And see, the units are watts. Watts are joules per second. So it's this many joules in 1 second. And no power plant can be compared to this kind of a power plant. It's just out of this world amount of energy. Remember, the distance between the sun and the Earth is one astronomical unit. It's 100 million miles. And even at that distance, you can't even look at it. I mean, you can look at it, but it's going to happen only twice in your life. The first time with the left eye, the second time with the right eye, and then you'll go blind forever. Do not stare at the sun for any long periods of time. You'll go blind. Seriously, no jokes. Same thing with telescopes. You point your telescope at the sun and you look through that telescope, you'll go blind. You need special filters to observe the sun, and the filters would be like a welding mask. The masks that are used for welding, that's a good, like enough protection to look at the sun. So let's take a closer look. What do we see? Is it on fire? Is that fire that is burning that you see on this diagram? Turns out it's not even close, because if you'll divide the amount of energy that would just generate fire by the total power output that we just discussed, the 3.8 times 10 to the 26, you will only get about 10,000 years of sunshine. Okay, 10,000 years of shine. And we know that the solar system is 4.5 billion years old and the sun is still there. So it's clearly not fire that is burning, something else. Is it contracting? That's another good question, and it was actually a very popular theory back in the days when people didn't know nuclear physics. Uh, the famous physicists Kelvin and Helmholtz really suggested that the sun is just contracting and it's gravitational potential energy that is converted into heat and radiation. Um, Remember that our theory about the uh, birth of the sun involves contraction of the cloud. The interstellar gas cloud contracts, and the gravitational potential energy is converted into spinning that starts moving, and it gets hot and it gets dense. That's where the star is born. But turns out that once the star is born and enters the main sequence, there is no more contracting. It's not the contracting process that really defines the energy production. Let's put it this way. So, uh, so your conversion of gravitational potential energy into thermal energy and other forms only happens when you have the process of the formation of the star. And once the star has formed and entered the main sequence, no more contraction. So how do we know it's not the case? Well, once again, the gravitational potential energy stored in the sun divided by the luminosity that we measure. Once again, luminosity, the total power output, and you have this crazy number. Uh, you're going to get about 25 million years of sunshine. Okay, million. Once again, remember that it's 4.5 billion years, which is like 1,000 times uh, more than millions. Um, so clearly not a match, and even geology helped us to overturn that theory by Kelvin and Helmholtz, because you find those meteorites that fall on Earth and you start dating them, and you'll see that they are way older than 25 million years. So you conclude that it's not contraction, it's something else. So when the sun was forming, yes, contraction. Once it has formed, no more. So what is it? It's the process that we call nuclear fusion. Be careful, it's fusion, not fission. Fission is splitting of heavier elements, and fusion is a squeezing of lighter elements, which is exactly the opposite. And it's the Einstein's famous equation that explains mass as a form of energy. So what the sun does, it loses mass. It converts mass into energy. And with that kind of a approach, you do the division of the potential energy stored in the core in forms of hydrogen and helium gases being converted one into the other and divide by the power output. You're going to get 10 billion years of sunshine. And finally, we have a good match. We have uh, good explanation for the age of a solar system. It matches the Nice theory for the formation of the solar system, and it matches the Big Bang theory for what's going on with stars in general. Once again, once you have stable fusion rate, because this rate changes over time. The sun, by the way, has increased its power output by like 30% since the process of formation, since it has entered the main sequence, and now no more contraction. So the sun just loses mass and converts it into energy. Uh, Remember the pillow effect from the gas giants? Same thing happens to the sun, because the sun is essentially another gas giant, and you have upper layers pulling on pushing on the um, layers that are close to the bottom, to the core of the sun. And with that gravitational contraction, you have enormous pressure and density needed for the fusion reaction uh, to go. And once again, it's not just temperature; it's also the pressure that is needed, the density, and you have enough, like good enough conditions to go uh, to to go through the nuclear fusion reaction. So two major forces um, are present in like within the sun. Of course, it's gravity that is trying to contract it to, towards the core. And then remember that the sun is gas, and gas has pressure, and pressure is force per area. So essentially, what you call pressure is just another kind of a force, the force of gases opposing the gravity. And this is your stable equilibrium. Equilibrium means balance. Every time someone says equilibrium, just think the word balance. So the sun is in balance between those two forces, and that's what keeps it stable over very long periods of time. There is a conservation principle in terms of energy. Remember, the total amount of energy is conserved, and yes, the sun generates energy through the nuclear fusion, but then it loses some energy through the process of so convection all the way to the surface and then radiation into space. So radiative energy balances uh, what we have produced in terms of fusion. Okay, the structure is pretty straightforward. We already discussed the solar wind. That's the outflow of charged particles. That's the reason for our northern lights, the auroras that you see in polar zones here on Earth. And that's what has stripped away the atmosphere on Mars. And that's the reason for Mercury to also be barren and no life. So solar wind is the energy that the sun releases from its surface, and it just goes in all directions, and um, that's what it is. The next layer closer to the surface is what we call corona, and you can see that the temperatures are crazy. We have millions of like degrees, but you can't really see it other than the conditions of total eclipse. Those halos around the moon that blocks the eclipsing sun. That's what you see as corona. So it's very hot, but extremely low density. So you can't really see it with your naked eyes. Uh, you just see through it. And then we go closer to the surface. The chromosphere is right in the middle between corona and the photosphere. The photosphere is the surface level that you can actually see with your eyes. Temperature drops. You can see it's not millions, it's just 10,000 to 100,000. But density grows. So in terms of total amount of energy, you have greater energy, even though the temperature is less. So finally, we reach the photosphere, which is the visible surface of the sun. And you can see that the temperature drops even further. By the way, this is the coolest zone of all the zones in the sun. See, it's in green, so there will be a question on which one is the coolest, and it's the photosphere that is the coolest. But once again, density goes up and up and up, and you can actually see that uh, with your telescopes. Once again, make sure you use protection, the filters, or you project the sunlight on a screen and then watch the reflected light, but do not stare at the sun with your naked eyes. You'll go blind. And the telescope also needs protection filters. Now we go deeper into the sun, and I've already mentioned convection. Convection is the rise of hot matter, and uh, hot matter rises and expands, cooler matter sinks and uh, shrinks. So it's ready to be heated again, and the cycle, see those circular-ish uh, processes. This is the interchange of hot and cold matter. So cold matter sinks, hot matter rises, and it's an ongoing process to transport energy all the way from the core to the surface. And then radiation zone, you have those photons that you generate through the nuclear fusion reaction, and they go zigzag. They collide with matter, transfer some energy, change their direction, and that actually happens for quite some time. You'll be surprised to know that it takes hundreds of thousands of years for those photons to find their way out of the sun. So the light that you see today has started inside the core of the sun hundreds of thousands of years ago. And finally, the core. This is the main uh, core for the power plant. That's where the energy is generated. Everything is generated inside the core only, at least for now, until the sun will become a red giant. Everything happens inside the core. Like all the magic is inside the core. Temperature is 15 million degrees, and it's not just temperature, it's also extremely high density and pressure. So the core is the main engine for the whole setup. It's the hottest zone, it's the most dense zone, and that's where the fusion is happening. Okay, this diagram clearly shows the difference between fission and fusion. So fission is splitting of a heavy element into lighter ones, and fusion is squeezing of lighter elements into a heavier one. It's exactly the opposite. And make sure you don't flip-flop them. For fission, it's what is going on inside nuclear power plants. You have uranium, you bombard it with neutrons, and that uh, uranium splits. And that's how energy is released. And inside stars, it's the hydrogen atoms that are squeezed together, and you have helium as the outcome, and energy is released in terms of photons because of such a reaction. Your question might be, okay, if we have hydrogen and hydrogen, they have the same electric charge, and you know the electric charges, like charges, repel. So how in the world are they capable of combining together? Well, you're right in terms of electromagnetism. You have the repelling force between like charges. But here comes the strong force, one of the nuclear forces, the strong force and the weak force. It's called a strong for a reason. It's much stronger than gravity and electromagnetic force combined. It's the strongest force of all, and that's why it's kind of easy uh, for this force to overcome electromagnetic repulsion. So fusion happens on a very small scale. You have, I mean, smaller distances. Everything is packed super tightly inside the core. That's why it's kind of easy for those atoms to get together and release energy from that process. Electromagnetic force is just not strong enough to oppose the strong force. And this is the main reaction. You have four atoms of hydrogen, and it's one atom of helium as the outcome. And what's even more important, it is the plus energy. So during this process, energy is released, and the overall loss of mass is about 0.7% less. So only 0.7% of a mass is converted into energy. But this 0.7% is what really drives the whole thing, because you have gazillion of those reactions in a unit of time and multiply this by a gazillion. So I'm saying gazillion because it's not even million, a billion, a trillion. It's just way more reactions than you can possibly find a number to. And you have enormous energy release, enormous energy output, which we discussed in the luminosity section. This is what's going on inside the core. This is what will be going on for another, what, 4 billion years. And this is the definition for what we call the main sequence star. If a star is a main sequence star, that's exactly what's going on inside the star. Now, let's say there is a rise in core temperature, and that means a rise in release of fusion energy. What would happen to the core? And there is a little mechanism, we call it solar thermostat, that explains everything that's going to happen. So the answer is the core would expand because it's getting hotter. Remember, hot stuff expands and cool stuff shrinks. So it definitely will expand. But after that, it's going to cool down. And the reason for that is because you can't really support, the sun cannot support its new size with the same levels of fusion. So this is what's going on. So let's say there is a rise in the core temperature. That means large increase in the fusion rate. So more and more energy is released. And because of that, the star uh, increases its size. It's not like a dramatic increase, like it's not a giant phase yet, but the size, the overall size increases. It's like internal pressure wins over the gravity. And then here comes the star with its new size, and the rate of fusion is still kind of, like there's like a limit to that rate, and you can't really support that new size with the same level of fusion for long. It's gonna happen for it's not gonna happen for long, and eventually it cools down and goes back to normal. And if there is a slight drop in the temperature, then the fusion rate drops, so less and less fusion reactions, less and less energy is released. So the core is gonna shrink. And if something shrinks, remember, there is a conversion of gravitational potential energy into, that's correct, heat. And that's how the core heats up again and goes back to normal. So no matter the change inside, the sun stays rather stable. Yes, there is a slight increase or decrease in size, but the thermostat process keeps it, uh, you know, kind of the same level with a little bit of a deviation from that norm. So you can think about your air conditioning or heater that you turn on or turn off, depending on the conditions outside. So the sun has this built-in thermostat that regulates its rate of fusion and core temperature. So yes, it takes hundreds of thousands of years for those photons to find their way out, which is probably something you didn't expect. It only takes 8 minutes for those photons to travel from the surface of the sun to the surface of Earth. But before you get to the surface, it takes hundreds of thousands of years. So what you see as the sun, I mean the light hitting us today has started way, way long ago. And it's the bouncing photons that are trying to find their way out. Okay, so for convection, that's how energy is transported all the way up to the surface. And you can see brighter zones on the surface. There are some pictures of the sun. Yeah, I have this one. Yeah, so this is the like a real life view of the surface. You can see brighter zones. Those brighter zones are hotter zones. It's just the gas that has arrived recently. And then there are darker spots. That's the area when the gas has cooled down and it's ready to sink back to the core. Okay, it's time to do some brief summary for what we said so far. Time for you to go watch the first part of the sun's episode from Crash Course Astronomy. So I'm pausing the lecture and you go watch the video, the first part of the video. Okay, here comes another problem. How do you know what's going on inside the sun if temperatures are 15 million degrees? There's no way uh, for us to, drop a probe into it and, measure the temperatures or the pressure. It's just no instrument can survive 15 million degrees. Remember Jupiter, our titanium probe, it was vaporized just right away. And the sun is even worse in terms of those conditions. So clearly there is a problem with uh, measurements. So what we do instead of going into the sun, actually, we observe the changes. Okay, it's the changes on the surface, and sun is not kind of just sitting still. There is like life going on. It spins on its axis, and by the way, the one period for the rotation is close to what we have here on Earth, like 30 days or something. And we use mathematical apparatus, the differential equations, to predict what's happening inside. The beauty of differential equations, if you know the correct equation and you measure the outer conditions, you can model what's going on inside with a very good accuracy. Um, we have differential equations of heat and mass transfer. We have equations for conduction, convection, all sorts of thermodynamics. So you don't have to send a probe directly into the sun. You just uh, model what's inside with mathematical apparatus and observations from the outer zones. And here comes the new, fresh idea on research, the newly discovered particles. We call them neutrinos, and they fly directly through the sun, and it tells you a lot about those the behavior of subatomic particles. I don't really want to go deep into that. It's still an ongoing research. We're getting more and more data from different kinds of experiments. It's very hard to collect those particles, but with some clever engineering ideas, more and more experiments just pretty much confirm what we already know. So there are no major gaps in our understanding and theories versus what is predicted by theories versus what we actually measure. So mathematical models of interior match the data on vibrations with a very high degree of accuracy. And this is how we study the sun. So you can see that the sun is not just sitting still and it's all calm and serene. We got problems. We have what we call solar storms, and they come as flares, prominences, and the worst is coronal mass ejections because it's plasma. And there is like, physics of plasma, which is a whole different, like a whole textbook, science textbook on its own, like the whole course that you can take if you're a physics major at the university. Uh, it's a rather complicated uh, organism. And because it's plasma, we have electricity. And because there's electricity, there's got to be magnetism. And those magnetic fields are not stable. They are not just constant. They're changing. And because of that, we got problems, especially on the surface level. It's clearly visible how uh, 1, 2, 1, 2. Sorry, the headset turned off. So it's clearly visible how magnetic fields are playing their own games with charged particles. And at some point, those loops can stretch out too far. They will snap, and that whole amount of plasma is going to be released and can travel all the way through space. And once again, this is your reason for northern lights that we see on Earth. Uh, and if it's a little bit of an ejection, that's fine. That's okay. We probably can survive that. But imagine a huge, like billions of tons of plasma being thrown outward in a random direction, and that hits the Earth. That's going to cause a huge problem for us here on Earth because we have satellites orbiting our planet, and that's sensible electronics. And we need satellites for navigation. We need power lines to transport energy on the surface. So all of those power lines going to be disrupted. Like forget cell phones, forget internet, Wi-Fi. None of that is going to survive a huge solar storm. So it all starts with those sunspots. They show the instabilities with magnetic fields. You can see that they're darker. That means they're cooler. So there are bright zones around the sunspot, but the spot itself is much cooler. This is your result of the uh, unstable magnetic fields on surface. Yeah, this is your side view for a sunspot, and you can see how the uh, huge arc of plasma is sucked out of the sun, and the gas is trapped inside. There's no way for it to escape the strong magnetic field here. And what we do here on Earth, we pretty much just count those solar sunspots. And if you count a lot of them, that means that the sun is not really stable. It's not in a good mood. So you might expect a solar storm at some point. If there are not that many sunspots, then the sun is kind of safe to, to it's not going to be extremely dangerous for quite some time. So counting the sunspots is somewhat an efficient way to predict a solar storm. Yeah, we measure the strength of magnetic fields with Zeeman effect. I used to have a question on Zeeman effect, not anymore, so you don't have to go that deep in terms of measuring magnetic fields with spectral lines, but that's exactly what astronomers do without actually getting inside the sun. And yes, you see those prominences. That's your outbreak of plasma into space. I do have a video. Is it here? Yeah, so there is the second part of the video from the crash course. Some good demonstrations on like the diagram really doesn't tell the whole story here. You really want to see how um, it is produced and eventually grows all the way to those enormous sizes. By the way, the size of Earth would be just a tiny dot. Like I would draw the Earth here, would be just a tiny little dot for comparison. This solar flare would just destroy everything on the surface of the Earth in terms of electromagnetism. So, pausing the video, you go watch the video, check those demonstrations, and understand how powerful the sun is, and can put us to our knees right away. Okay, one more story about how we observe the sun is the stereo mission by NASA. And the idea here is to be able to look at the sun from all the perspectives. Because if you're here on Earth, then you can only see one side of the sun, and you will never be able to see what's going on the other side of the sun. And if you want to predict the solar storm, you really want to take a live view on both sides. And the stereo emission does exactly that. It provides us the view from the back of the sun as well. Because if there is a solar storm, you definitely want to prepare for it, and it will take a few hours for that plasma to travel from the sun to Earth. And by this time, we can, make some preparations to survive the collision uh, with that huge stream of solar particles. So check out the video. Pausing the lecture. Okay, couple more slides. This is a clear pattern that you see in terms of number of sunspots. So you count the number of sunspots, and you can see that the sun is more active, less active, more active, less active. Uh, because those sunspots really allow us to predict the instabilities, like the amount of instabilities on the surface. And fun fact, a lot of conflicts, a lot of wars here on Earth are kind of connected to the same cycle. Uh, might be just a coincidence, but some major conflicts happened when the sun was very active, and many people would find a connection, say, "Oh, we're depending on the sun," and whatever. It's just unfortunate. That's just the nature of human beings. We can't live in peace for long, which is constant fight and struggle. Anyways, you can see the 11-year cycles, the patterns for the sun being not very active or extremely active, and the number of sunspots clearly show a pattern. And yeah, as you watched in the video, the dynamo machine, everything is not stable. Your equatorial zone rotates faster, much faster than polar zones, and that's what create that is the reason for creation of those instabilities in terms of magnetic fields. So it's still an ongoing process. We're still modifying and making our models better and better. Like I said, the physics of plasma by itself, with all those banana instabilities, it's just one hell of a ride, and uh, a very interesting science, but takes very advanced mathematics and understanding of those processes, electromagnetism. Uh, we're not going deep into that, but understand that the sun is not stable. It's not like just sitting still. It's like a living thing with its bad days and good days. And once again, it's an ongoing research that we still try to, understand what's going on inside. Okay, that's it for the sun. The very interesting chapter 12 is coming. We will summarize all the stars based on what we've learned in this chapter as well. So stay tuned for chapter 12, HR diagram, all the fundamental properties of stars. That is what astronomers really do on a regular basis. So consider this as just a brief introduction to stars, because the sun is our own star and we want to know what's going on. For chapter 12, you'll gonna learn uh, very interesting facts about stars in general. So I'm gonna stop it right now.